Hi, my name is Riley Fink. I'm originally from Boulder, Colorado, and I'm majoring in math here at Santa Clara with an emphasis in applied mathematics. My thesis focused on binary matrices and the swap algorithm. Binary matrices are matrices where the entries are only zeros or ones. I studied row and column sums of these matrices, where you simply add up the number of ones in each row or column to create a vector, where each vector entry corresponds to a sum of a row or a column. We can expand this idea to other slopes of lines beyond just horizontal and vertical. For instance, we can imagine layering lines of slope 1 or -1 along the matrix in order to find diagonal sums. We find these sums as if the matrix is repeated periodically. So you can imagine another copy of the matrix right next to the original matrix. So the parts of the lines that stick off the matrix are actually going on to the matrix on the other side. So there are two movements called interchanges that we can perform on these matrices without altering certain sums. The first is a standard interchange where we find a checkerboard-like pattern of ones and zeros and switch each entry to become the other number. So if it was a 1, goes to a 0 and vice versa. Doing this creates a new matrix, but the row and column sums are still preserved. A slightly more complex type of interchange is called an octagon interchange, which not only preserves the row and column sums like the standard interchange does, but it preserves diagonal sums as well. We can use these interchanges to create two matrices that have the same row, column, and diagonal sums, as well as the same sums along other slopes by kind of like stamping these interchanges. So this is what you see in the image here, where red and green represent a 1 and 0 respectively, and then the other matrix has the opposite, and then all of the white spaces are the same on either matrix, but they could be ones or zeros. It doesn't really matter. And then for some applications, it's useful to select a random sample of a matrix with specified row and column sums because it can be too time consuming to try to list out all of the possible options for matrices that fit these sums. So as part of my project, I coded the swap algorithm, which takes inputs of row and column sum vectors, which you see here on the right, and then it generates an example matrix by creating a maximal matrix, which is what you see in number 1, where everything in the row is just pushed as far to the left as it can be. And then it goes through and corrects one column at a time until it arrives at what you see in number 2, where now we have row and column sums correct. Then the entries are interchanged using the standard interchange by random selection, which results in an essentially random matrix that still fits our specifications. So that's what you see in number 3. Which is a different matrix from number 2, but still satisfies the row and column sums. There are other algorithms, such as the rectangular loop algorithm, which gives similar results. However, comparison across these algorithms and their convergence speed has not really been explored in depth, so that could be something to look into further. And then I also just want to thank my mentor and reader, Dan Ostrov and Howard Levinson, for helping me on this project. Thank you.